Am I audible? Yeah. Hi, everyone. Let me thank the speakers and the organizers for giving me this opportunity to speak here. So today I'll talk about chaos in fully developed turbulence. This is a joint work done with Oikku, who is a master student at ISAR Kolkata, Sugan, who is now a postdoc at Johns Hopkins University, and of course Shubhra and Samriti. So let's start. Okay, so we often hear this thing that turbulent flows are chaotic. But what do I mean by that? So for finite dimensional dynamical system, the notion of chaos is very clean. So you start with very close trajectories and you allow the system to evolve, and eventually the trajectories will separate. When do I say that the system is chaotic? When the separation is exponential separation. What do I mean by that? If I just zoom in at some point of the trajectory, so initially if I start with the delta zero separation, after time t, the separation will be delta zero to the times exponential lambda t, and this is for short time. So if we have this particular kind of trajectory separation, then we call that system a chaotic system. And this lambda is known as the Lyapunov exponent, which characterizes the degree of chaos. The bigger the lambda, the more the chaotic, the system is more chaotic. But this approach becomes a bit non-trivial when one talks about continuous systems or infinite dimensional dynamical systems. So let's take the turbulent flow and let's ask this question, how chaotic the flow is. So one approach is the Lagrangian viewpoint. So you put tracer particles in your flow and then measure how the tracer particles diverge in time. This is one approach. Other approach is you completely bypass the concept of trajectories. So you look at the fields. So you take one system and a perturbed system and you look how the fields diverge. So in this work, we'll take this second approach and define something which is an analog of classical decorrelate, which is the analog of classical decorrelators, and ask these following questions. How can we characterize Lyapunov exponent in turbulence? And what is the Reynolds dependence of the Lyapunov exponent? And what is the mechanism of chaos? Okay, so let me first set up the problem. So let's say there is a field U, which is a solution of Navier-Stokes equation. At some time t0, I make two copies of the system. One, I evolve as it is. Other system, I perturb a little bit. Then see what is the difference field, how the difference field evolves. And our definition of decorrelator is this quantity, is the volume average of this difference field squared. So then this phi t is a purely function of time. So if that function grows with time exponentially, then we can say, okay, there is a notion of Lyapunov exponent, there is exponential growth. So before looking at the results, let's see what we know trivially from this object. So what we know trivially is if we just expand this quadratic power, we'll see this first two terms, they're nothing but the mean kinetic energy of the system. Then there is a correlation term. And if the system is chaotic, after a long time, this system will decorrelate and this correlator will be zero. So naively, one may expect that at long times, this phi will have the value of twice the mean energy. So let's see if we see these things or not. So we make again two copies of the system and we plot this difference squared. So you see in the center, there is a small blob. That's the small perturbation that we have given. Now we run this thing. So as time evolves, we see that perturbation spreads and then the perturbation grow in magnitude. You'll soon see the growth in the magnitude. Now you see the magnitude grows. So there is a growth of the perturbation for sure. Okay. Then now we look at the volume average quantity of this perturbation, and we track that quantity in time, which is precisely the decorrelator, and plot in the semi-log scale. And you see there is a clean exponential growth. So that's a very good news because we have exponential growth, so we can talk about Lyapunov exponents. Okay. So before commenting anything, let's go back to the equation for this phi, for the decorrelator. What we can say from the equations. So basically the idea is you take two Navier-Stokes, identical Navier-Stokes for two different systems and subtract them and try to write down the equation for delta U square. There are many terms. This S is the strain rate tensor. This is the dissipation term, and this is coming from the forcing term. There is another term here which comes from the solving the pressure-Poisson equation. But finally, after all this mess, at short times, it reduces to this very simple looking equation, at least simple looking, not simple, but simple looking. So the first term is this, second is this, and there is a forcing term, which one can ignore at short time, because there is this is second order small quantity. So we have this nice expression. Okay. Now, let's do another verification that this is indeed true, this expression, and one does see an exponential growth. So if this has to be this is an exponential thing, so this object should be some factor multiplied by the phi. Then only one sees an exponential growth. So we computed all these quantities numerically and we plotted it. So do we see a plateau? So this is exactly this first term divided by phi, the second term divided by phi, and the full thing divided by phi. So the top thing that you see is the first term. The bottom thing is the second term, and this is the combined thing. So this is precisely gives this plateau, gives the Lyapunov exponent. Another interesting thing, which is kind of intuitive, you see for the first term, the Lyapunov exponent is positive, where basically the strain rate is amplifying things, whereas the second term, which is the dissipation, analogous to a dissipation term, it has a negative Lyapunov exponent. This is kind of intuitive because Laplacian has a smoothing effect. So whatever disturbance I put, it will try to smoothen out the flow. That's why there is a negative Lyapunov. Okay, so things are consistent. Now we can look for the Reynolds dependence of the Lyapunov. So we redo this simulation for different Reynolds number, and we see there is the growth rate changes or the Lyapunov changes. And so one can extract these Lyapunovs from fitting this curve as well as from this plateau, both ways. So we define two things. This lambda DNS is extracted from this one, and lambda is extracted from the plateau. So before we look at the exact dependence, is there any prediction? What do we expect? So there are few dimensional arguments and some phenomenological arguments which date back to Kolmogorov's work and Ruel's work, that the dominant Lyapunov exponent should be related to the fastest time scale of the problem, and that goes as square root of Reynolds. This is a phenomenological and a dimensional thing. So the question is, do we see that in the numerical result? The answer is we don't exactly. So the numerically, it shows the Lyapunov grows as Reynolds to the power 0.59 instead of square root Reynolds. Okay, so is there any way we can massage the equations that we have to get something like this? So again, we go back to our equation. So the second term is a sort of harmless term that we already saw, that is a negative one. The problematic term is this one. So this, what one can do is decompose this term in the eigenbasis of the strain rate tensor, and then you have three terms at every point in your velocity field. Now the question is, can you sort of fish out one term from this by arguing that one term is the most dominant term? So in this term, use this Ni square, they are basically the direction cosines of the perturbed field projected along the eigen direction of the strain rate tensor. So you plot the distribution of this Ni square to see if one term is dominant, and you will see this third eigenvalue, the third term, which corresponds to the third eigenvalue of the stress rate tensor, that's the compressible eigendirection. You see, that's the dominant term. So we can safely approximate this whole thing by the one eigenvalue, by one term only. Now, if this is true, and we can show that this gamma 3 scales as Reynolds to the power 0.59, then our problem is solved. We can say, okay, look, because gamma 3 scales as Reynolds to the power 0.59, your Lyapunov scales as Reynolds to the power 0.59. So let's try that. This plot I have already showed. Now we plot this eigenvalues, the mean eigenvalue, mean of the eigenvalues of the strain rate tensor, the compressional eigenvalues. And it shows not the Reynolds to the power 0.59, but the square root Reynolds, which was the mean field theory result. Okay, that's good and bad at the same time. But then whenever one talks about the mean of a certain quantity, one should also look at the distribution of these quantities. So point-wise, there are these eigenvalues. At every point in the flow, there is eigenvalue. So when we plot this distribution with the Reynolds number, we see the mean is shifting. That has a scaling of Reynolds to the power 0.5. Also, the standard deviation is also changing. It's broadening with Reynolds number. So also it's interesting to see how that standard deviation scales as Reynolds number. So when we do that, these diamond markers. This is the standard deviation of gamma 3, and that not only follows the Reynolds to the power 0.59 scaling, but the values are suspiciously close to the Lyapunov exponent. So this is a bit interesting that so whatever we found that the governing mechanism for the chaos is the compressional eigenvalue, but the mean of that eigenvalue governs the mean field theory result, and the standard deviation of the eigenvalue gives all the intermittency correction or the corrections coming for fluctuations. And for this particular case, since the fluctuations are dominant or has a stronger scaling than the mean, so this is what one always sees in the numerics. One never sees this square, the mean field theoretic result. So yeah, yes, so that's how I summarize. So we just revisited the problem of chaos in fully developed turbulence. How does one define it? What's the mechanism of it? And the final takeaway of this work is the main thing which governs the chaos is the compressional eigendirection of the strain rate tensor. And the mean of that eigenvalue will give you mean field theoretic result, and the standard deviation gives you the correct results, which is really the fluctuation of the eigenvalue of the strain rate tensor which governs the chaos in fully developed turbulence. Thank you.
Thank you, Ritwik, for the interesting talk.
Yes.
Questions?
Hi.
Yes.
Thanks for the nice talk. I just want to understand how this kind of exponents change with the whether you solve the 1D Navier-Stokes or 2D, 3D, how it changes across the dimensions.
We haven't studied that because for the 1D it's slightly tricky. 1D, if you the analog of Navier-Stokes in 1D is Burger's equation, because kind of we are dealing with incompressible Navier-Stokes. So if you retain that incompressibility condition in 1D, it's a boring thing. So analog is Burger's equation. It's boring because there are shocks. Any perturbation you do, finally it will end up in shocks. 1D interesting part is what Aniket is doing, is some stochastic forcing. There also you see this kind of things. Okay. 2D, again, it depends. 2D flows are also slightly trickier, whether you want to ask the question in forward cascade or in inverse cascade. But I believe it's not as chaotic as 3D, for sure.
Also, just one concern. Through the Lyapunov exponent, can one comment on when the about the critical Reynolds number at which the flow become transit to the turbulent flow? Such a thing can one quantitatively say from the Lyapunov exponent itself from here?
Well, if the flow is too viscous, you won't even see a growth.
Yeah, exactly. So
you won't even see.
So with respect to RE, you're seeing that kind of a scaling and so on.
Yeah,
so
all this scaling.
The question is, can you get a critical value at which the lambda just stops?
Well,
sorry, lambda becomes.
Yeah. So the kind of analysis that we do for if the Reynolds is sufficiently small, you don't even see a growth. But I'm not sure whether you'll find a critical Reynolds where before that Reynolds we'll see no growth, and after that you'll see a nice growth. I'm a bit worried about exactly you can pinpoint that critical Reynolds. I'm not sure about that. Okay. Rajesh.
I had a few questions.
Yes.
So the first one is, if instead of perturbing in physical space, you perturb in momentum space.
Yeah, there is a similar. I mean, this exact study is not done in momentum space, but there are many works which perturb in momentum space, and so people generally don't do a sum over all the modes, but they see mode-wise decorrelation, as well as they take a sphere and do a surface integral, then see at the mod k. For each modulus of k, they see the decorrelation. The results are, I mean, one can also talk about Lyapunov in momentum space.
The second question is, if I coarse grain the Lyapunov exponent over your box, will that distribution multifractal?
No. Okay, that's an interesting point. So one can do, I mean, I haven't showed that, but where is that thing? So I haven't talked about local Lyapunov, but since you have these terms, and these are volume integrations. So the integrands, in some sense, represent the pointwise Lyapunov. And these things have a very weird distribution. For example, the first one has a, if I remember correctly, is a more or less exponential, but the second one has a power law tail with 1 over lambda to the power 4, I guess, where the lambda is Yeah, 1 over x to the power 4 is at the tail of the distribution. They had very peculiar distribution. And the question whether they're multifractal or not, we don't know.
I see. And the last one is these alignment probabilities. They look flipped of the probabilities when you align the vorticity with the strain.
Oh, okay. Yeah. So, but this is okay. This is slightly tricky because this is the alignment of the perturbed field, not the real field. So it's tricky to intuitively visualize.
Right.
Because we're for sure the compressional eigendirection of the main system, but the alignment is happening in the perturbed field.
And the S you take is the real field.
Exactly. So that's the final result. So you don't even need the perturbation field. You can just talk about the Lyapunov from the your main field strain rate tensor. So that's what governs the whole thing.
If I take the perturb field to be one snapshot evolution of my real field, like my delta U is just U t plus delta t minus t.
Yeah. I don't think this changed because of the evolution, because because we tried different initial perturbation, the results were same. But that's a very specific kind of perturbation you're talking about.
Right.
I would naively say it won't change, but I don't know.
Okay. Thank you so much. And Stitadi might have some online questions which we can address.
Yes.
Yeah. Yeah. So so there are these 2D or 3D laminar flows which are also considered chaotic, like Galloway-Proctor and so on. And there, if you because they're laminar, which means that you can have them at high enough viscosity also. There, if you perturb like this, I would naively expect the perturbation to die off very quickly.
Yeah.
But they are considered chaotic in the Lagrangian sense. For instance, if you throw tracer particles, you see them diverging as far as they want. So then, yeah. So how does this?
No, I mean, yeah, I understand. How do you reconcile these Lagrangian viewpoints? And this is slightly tricky because here you see the main result of this work is you find a growth of Lyapunov, which is more than 0.5, which is more than the mean field theoretic result. But there are Lagrangian results which shows the growth should be less than 0.5. So it's not. I mean, there are good, very clean results. So it's not very obvious. How do you reconcile these two viewpoints? At least I don't know. Yeah, thank you. And
okay, let's thank Ritwik again.
yeah, thank you.